Okay, perfect. Okay, so today I'm going to be giving a talk about Icicle and about how you can use GPUs with your ZK provers. And by using GPUs, you can basically attain really fast ZK proofs and scalable ZK proofs. So I'll begin by introducing myself in Ingonyama. So my name is Emmanuel Segal. I'm a product engineer at Ingonyama. Ingonyama is a hardware acceleration company for cryptography, and we focus primarily on ZK and on fully homomorphic encryption, so FHE. But in general, we design hardware systems, so GPUs, FPGAs, ASICs, and we do a lot of research into the mathematical primitives that are behind all these cryptographic algorithms. So that's a brief introduction to Ingonyama. So today we will speak about Icicle. So Icicle is a open source uh, GPU library. It's written in CUDA, and this library implements all the primitives required to write a ZK prover. So for example, we offer MSM, we offer NTT, we offer different like curves, point operations, elliptic curve operations, polynomial operations, Poseidon hash, everything that you need in order to construct a ZK prover system. We offer 3 APIs that developers can use to access all of these accelerations. One is a CUDA API, so it's a C++ API, and then we also offer a Rust and Golang APIs. So by using Rust and the Golang APIs, you can basically just call this function like named MSM, and that function triggers the operation on the GPU, and you don't really have to know anything about what's happening behind the scenes to benefit from this almost instant acceleration. Um, so why did we develop Icicle? Well, we've been researching snarks for a while, and we found that almost all of the snark frameworks are implemented on CPU, and CPUs they're pretty powerful, but they're not the best at extremely parallel operations. So if you look at ZK systems, for example, and you look at the core mathematic functions like MSM and FFT, you see that these functions can be extremely parallel friendly. GPUs are basically the perfect hardware for parallel computation. Um, they've been like AI uses GPUs like everywhere basically for its advantages in parallel computation. And GPUs are also pretty cheap compared to ASICs or FPGAs. Also, if you reference the like Z Prize of 2022, 2023, you, there's pretty good uh, case studies there of how GPUs can be used for accelerating MSM and NTT. So let's speak a bit about GPUs and why we chose GPUs for Icicle. So one, like I stated, GPUs are extremely parallel friendly. Like they're basically designed for parallel computation. GPUs are also extremely easy for developers to use. NVIDIA designed an entire software stack just for GPUs, so developers can basically use C++ code, Rust code, Golang code, pretty much any language that they want to simply call GPU functions. GPUs are also extremely competitive in terms of power to performance compared to FPGAs. I'll show that inside another slide. And also they're way cheaper than FPGAs. So for example, if you compare the like 4090 to a FPGA in the same class, it's about 3 times cheaper. So at Ingonyama, we actually developed this like metric for measuring power efficiency. Uh, we call it GMM, like watts per GMM. So GMM is basically modular multiplication. This is a core function that happens basically in MSM and FFT. So giga MMM is basically a billion modular multiplications per watt. So the lower is better, right? So for example, if we look at the like L4 GPU, we can see it basically is like 5.31. And if we look at other FPGAs, we can see that most of them are way less efficient. Now, when you look at these retail GPUs, you see that they are less efficient than FPGAs, but if you look at the actual price, these GPUs are more than 3 times cheaper than these FPGAs. So we think that GPUs have an advantage when it comes to power efficiency and price. There's also this article that I linked here that I think that you should read after this talk. It goes in depth comparing these differences between GPUs and FPGAs. So we will now speak about some Icicle integrations. I'll go over how we use Icicle. I'll explain a bit about the like performance boost that we experienced after integrating Icicle into some mainstream provers. We will be covering 2 integrations. One is an integration with Halo 2. It's a integration that we did with the team at Icicle. This integration is still work in progress, so I will only display our initial benchmarks for our very first version of the integration. But I will also go into an integration between Icicle and Gnark. Gnark is a prover framework from a Consensus. With them, we also had this official collaboration, but our prover is complete and it's in production. So there I will actually go into the code and into the final benchmarks. Oh, and also, if you have any questions, feel free just to interrupt me. Yeah. Okay,
Yeah, what
so
does Icicle stand for?
oh,
I'll just
for
put
nothing. It actually doesn't stand for anything. We just we actually called we have two libraries. We have Icicle, which is the GPU library, and we have Blaze, which is the FPGA library. So it's like ice and fire. Like there's like no acronym here, unfortunately. Yeah. Yeah. So the first integration is with Icicle. Uh, Again, like I can't go into the code here because it's still work in progress, but these are the results from an initial very trivial integration. So this integration took I think like 1 or 2 days, and it's basically a drop-in replacement where we don't optimize for GPU. We just like replace the function. So if it said like arcworks.msm, we just replace it icicle.msm. So with a simple drop-in replacement of MSM, we experienced basically like a 30x improvement on some of the on some of these MSM operations. Now, you see, different MSM operations you have different sizes. So if you actually look at this table here, we we basically log like each part of the Halo 2 algorithm, and we log like the times that it took to do each MSM. So you can see here for example, this is the like GPU time, and this is the CPU baseline time. Our GPU was a 4080 RTX, and as you see for example, when we calculate permutations, one MSM here took like 0.1 seconds versus CPU where it took 4 seconds. So this is just a simple drop-in replacement, no other optimizations in the design of the prover. Yeah, so you see like the total proof time was cut down to 78 seconds versus 170 seconds. Now I'm gonna go. Okay, so that's all that I have to show for the Icicle integration for now. But we will dive deeper into the Gnark integration. But before that, I want to go over some terms just to like in case some of you are not that familiar with GPUs. I want to go over some core ideas that I think are important for developing on GPUs. So the like first idea is the idea of device versus host memory. So host being your machine, your CPU, your RAM, and device being your GPU and the GPU's RAM. So each GPU actually has RAM inside it. So if you buy, let's say, an RTX 4080, you have like a 6 GB version, a 16 GB version, a 24 GB version. So that's what GPU memory is. And then you have what's called a PCIe. So if you ever saw or connected a GPU into a machine, there's these little slots, and you actually connect your GPU into the motherboard. So PCIe is basically the like communication between your host and your GPU. Now, when you design GPU software, let's say that you're designing the ZK prover and you generate this witness on CPU, and you have all these scalars and points, and now you need to do MSM on GPU. So there's this phase of transferring memory. So you basically transfer the memory from your RAM to your GPU memory. And this can cause latency. So for example, if you if you transfer data frequently between host and device, you will actually slow down your approver because you have to always copy this memory back and forth, back and forth. So when you design software for GPUs, it's really best to design your algorithm on GPU where you have to load in the like data initially, then you do all the computation or as much computation as possible on GPU, and only then you offload the result back to the host. So so yeah, that's the first point. Oh, also, does anyone here know what CUDA is? Like, is there anyone here who does not know what CUDA is, or should I just explain it? So, another important element for GPU development is a CUDA. So, for example, when you look at all these core functions like MSM FFT, our team at Ingonyama implemented these algorithms in CUDA. CUDA is this language developed by NVIDIA that allows you to easily write code to run on GPUs. So basically, Icicle implemented MSM, implemented NTT in CUDA on the GPU. So I'll go over Gnark real fast if you're not familiar with it. Gnark is this framework. They offer different provers. It's written in a Golang. They have a Graph16 prover. They have a Plunky prover. I think they have a couple more. It's and also Gnark allows you to actually write circuits in Golang. So it's like Circom where you can write your own circuit, or like Halo 2. You actually can write your own circuits in Golang using Gnark. So let's go over the like actual architecture of our integration. So on the host side, you have the like original Gnark code, and you have Gnark crypto. Gnark crypto is this cryptography library developed by the Gnark team, and all the like cryptographic operations occur in Gnark crypto. So you have like elliptic curve operations here. You have MSM, FFT, uh, different point operations, etc. And then you have Go Icicle. Go Icicle is a Golang binding that basically exposes a Golang API similar to the Gnark crypto API, basically a classic like cryptographic API. But behind the scenes, it will call the CUDA code, which runs on GPU. Okay, so this is your binding. This lives on the CPU, but this will trigger GPU code for you. So as a developer, you will only need to touch Go Icicle. You won't need to actually touch any CUDA code unless you want to do like custom optimizations at the algorithm level. Okay, so at the first phase of actually designing our Gnark Icicle integration, our research team really dived really deep into Graph 16 and really broke down this algorithm and identified the locations of what needs to be accelerated. So as you see here, we have like FFTs, we have MSMs, and here we have this function named H function, which I'll speak about in a moment as well. What? Siri heard me say something. Like spoke, sorry. Okay, so here is a link, but I will send you. I'm actually going to send you guys this like you need to learn about Icicle and all these integrations later. So let's dive into what this integration actually looks like. So first we have a setup phase. So if you remember, we were speaking about copying memory from host to device. So this is the like setup phase where we actually allocate on GPU all of these points and scalars, and we do different like optimization, like optimization, like we filter out 0 points or stuff like that, and we also like pre-generate some some factors for FFT. So I don't know if you guys can see this well, but do you see here this like function named go dot CUDA mem to device? So basic phase is we will copy all of all of the all of the initiated to setup phase. You can just think of it as to the GPU. Now, and the proof function arrives MSM code. As you see, it the like cryptographic CPU device or like MSM on GPU to the data that we copied to the device previously. So this data is already on device, and inside our Go code, we really need to make this very minimal change, where we just pass these pointers instead of calling this function. So it's a very similar code. We just swapped out their function with our function, and we have this setup phase. So you basically do this to every single MSM, and you get an MSM acceleration because now you're not copying any data, and you're running the entire MSM on GPU. Now, a couple points about MSM. MSMs are actually extremely like memory intensive. So, for example, because we have all these points on the GPU, we actually found that we cannot run on a single GPU multiple MSMs in parallel. So we have to we actually do MSMs sequentially and not parallel like they were done on CPU, but we still get a performance boost. Now, what's important is that if we have multiple GPUs, we can actually do one MSM per GPU, and then we can really accelerate like um, MSM, because basically you have these MSMs happening in parallel, and each one is like 15x faster than CPU. So you really have very fast MSM execution if you have multiple GPUs. Now, I told you guys about H function. So H function is actually an interesting, like, I guess, case study for how you should write proper GPU code. So if we look at this section of the algorithm, we have these FFTs. Then we take the results of these FFTs and we run them through H function. And then we take the result of H function and we do an inverse FFT. Now, we all know that these FFTs occur on GPU, but this isn't implemented on GPU. This is implemented on CPU. So what would happen here is we would do this computation on GPU, we would copy it to CPU, then we would copy it back to GPU. This actually would hurt performance and actually be slower than a CPU implementation. So Icicle offers all the functions that you would need to actually implement H function on GPU completely. So you can actually, with Icicle, implement these FFTs and this custom H function all on GPU. So this is how it's actually done. This is the original code. You have this FFT inverse, then you have FFT, then you have H function, and then you have FFT inverse. So the first thing that we did, we created these pairs. So you have one uh, FFT inverse, and then FFT, and then we run three of them on GPU in parallel. So instead of running 1, 2, 3, 1, 2, 3, we run like 2, 2, 2, and we run them like each one on like a separate thread, and each thread is calling the GPU with like both of these functions. So that's the first optimization. Second optimization is this polyops function. Polyops function is basically multiplication, subtraction, implemented on GPU. So we have these functions implemented in CUDA, and what happens here is that this is occurring on GPU, and then you just pass the pointers, and then you don't need to copy any data back to CPU. This also occurs on GPU, and then you just pass this pointer here to like a device, and then this will also occur on GPU. And then only the results can be copied back to CPU if you need to do that. So the results of this optimization with Icicle and GPUs can be seen here. So we benchmarked it on a on a circuit, which is 2 to the power 23 constraints. We benchmarked it on a couple different computers with what like first two have very powerful CPUs with 24, 32 uh, with like 8 or 16 different cores. And then we also benchmarked it on the 3090 Ti and the 4080 Ti. Here are the, like the in detail uh, results. So we went from basically 7,000 milliseconds down to 1,400, and our speedups for NTT were times 15, MSM times 4. This is running on a single GPU, by the way. So, for example, if we put every MSM, or even if we just added one more GPU and split the MSMs between the GPU, we would see a times 8 here. And the general prover speed increase was times 5. And this was on a Brevis circuits. Yeah, and now everything here is also open source, so you guys can actually look at this implementation. And if you want to, you can even use, without having to touch Icicle or without having to touch any GPU code, you can use the Gnark prover today with GPU acceleration. Yeah, so I think like that's really what I wanted to show you about this integration. Now I'll I'll really fast just like cover like what we offer at Ingonyama to members of this hacker house. So Ingonyama is an open source company, and all of our research is open source or open sourced eventually. All of our code is also open sourced eventually. All of Icicle is developed in public, and we really thrive on collaboration and on all of the ethos of like open sourceness. So we offer technical support. uh, we have this dedicated Discord channel. I actually sent in Telegram a link to join, to send me your Discord handle, so I can add you. And then our engineers and researchers can help you with technical support, research support. We also can offer you hardware. So if you don't have a GPU and you want to research how you can, like, I don't know, like optimize for GPUs, or you want to experiment with GPUs, we can give you access to GPUs or FPGAs. And we also have what also, if you're interested in researching anything long term, yeah, if you have this very interesting problem that you want to research in the domain of hardware acceleration for ZK, like feel free to reach out as well. we support like long-term research efforts. We also have all of our material is also translated to Chinese. So we actually have this link here to all of the documentation in Chinese, and I think also all our blogs and research papers as well. So this link actually expired. I was using a free version, so I will send the like correct link to all of the resources. Yeah, and we were really excited to support you guys with anything that you need for your hacking adventures. Yeah, thank you.
So I have a question. Can you hear me?
Yes,
So did you integrate with Hello 2?
yes. So the like branch is actually public. I can send you the branch that we're currently working on for Halo 2 integration. We integrated with EZKL's Halo 2 fork. So you can actually use. I think our integration is usable. Like the branch isn't broken, so you have partial GPU acceleration. Yeah, but it.
So the second question, sorry, you can continue.
No, it's okay. Sorry, it's okay.
So the second question is, I've been using the SPPRK repo to accelerate Hello 2. So have you done some comparison between Spark repo and your your implementation?
Do you mean between like Spark, the like cryptography library?
Yeah, SPPRK. The
Yeah.
this is
We
also a
have
GPU acceleration.
yeah we have benchmarks. I can send them over. I have to ask the like team for them, but if you want to see comparison, I can provide this.
Yeah,
I'll listen. Let me write
you
it
can you
down.
can you can,
Let me just. I'll like write it down and I will send you this link. Okay. Because I don't remember the exact comparison off the top of my head.
okay. Thanks for your time. And the last question is, when I do the GPU acceleration, I found the same problem as yours. That it's a memory problem. For example, I've done a big Merkle tree hit with a large hit, and the memory used that was about 200 RAM. So I see you told you have done some optimization on memory, so you can divide the memory uh, to GPU and down the sections. So I was wondering how you do this, and is the repo has a repo open source? Yeah.
Yes, the like, repository is open source. I can send the like link to it. How we did it is really during the like setup phase. Let me send you the actual link. Our research team is also looking into, I think, what you're speaking about in Halo 2, right? Like with constraints and when you basically
Yeah.
run out of memory with.
Yes.
Yeah, so we're actually researching that now. I can't like that's kind of internal like research at this point, but I can put you in touch with Kartik, our head of research, and he can like maybe share a few what he can share, because we're actually like researching that with Icicle now.
Okay. Thank you.
Hey, Manuel,
Any-
great talk. This is Saurabh. I have a few questions. So, firstly, can you shed some light around the resource utilization, the occupancy metrics, especially with these entity primitives, right? Are you closing in towards 100% optimization? How close is it?
You mean the like how like what do you're speaking about like how much of the GPU is being utilized during runtime?
Exactly, yes. Comparing
Yes.
for both these MSMs and entity.
Yeah, so right now we're actually looking at it's 100% basically. So for example, when you run large entities, like okay, entities you can run multiple on the same device, but I think like if you run 3 or 4 at 2 to the power of 23, you actually achieve like full occupancy of the device. The MSMs are more demanding, and a single MSM will actually use the entire device.
That's wonderful.
So
Also, one more follow-up
100.
question. Yeah, please go on.
No, I was just saying so yes, it's using 100% of the GPU.
Got it. Okay. My other question was around do you see some sort of vendor lock-in happening with
Yeah. Okay. So
NVIDIA? Do you
sorry, it broke up. I didn't
can
hear what you were saying.
expand this to maybe the future because the CUDA this as maybe.
1 second. Sorry, it broke up. Something happened. It just broke up. I couldn't hear you. I turned off my camera because I don't know like why it broke up. Can you repeat
No
your
worries.
question?
Yeah, absolutely. Sure.
Sorry.
So I can see a little bit of tight coupling with NVIDIA and the CUDA framework with Ingonyama. So do you see this do you see this being supported to maybe AMD GPUs sometime in the near future?
Okay, yes. So yeah, this is okay. We would want to support every single GPU platform, right? We don't like we're not necessarily trying to stay with NVIDIA only. The issue with this is really, I guess, like it's time consuming to re-implement in like every language. So like you have to implement it like for AMD for like AMD inside different languages because there's like no way to compile NVIDIA like CUDA code to AMD efficiently. There's like different hacks that you can do, but it's not the most efficient way to do it. And like if you want to support Mac like M1 chips GPUs, then you need to write it in like metal. So currently, that's not really on our near-term roadmap. But if you're interested in doing that, then that's something that like would be interesting. Yes.
Um, Emmanuel, just one more question. Are you guys also looking into client side proving and web GPUs?
Yeah. So one of the bottlenecks here is really memory. So for example, for large circuits, you need a lot of memory. So you need a pretty serious GPU. You know, like an RTX 3090 with like 16 gigabytes of RAM, let's say, right? But for smaller circuits, you could definitely use client-side GPUs. You would like at this point in time, your client would need to have a NVIDIA GPU. So for example, it wouldn't work on like the M1 GPU. So that is a limitation. It's not something that we're focusing on currently, but we are researching and we actually are running some tests with like large data centers. for scaling for scaling like ZK proofs at a data center level. So no, like we're very interested in web GPU. We're very interested in client side proving, but currently it's not something that we're extremely focused on.
So yeah, I will have that. So I have two questions. So the first one, so in the context of ZK hardware acceleration, so what do you think? So the most least and most useful part in a GPU. So like the GPU has a lot of ALU, right? But maybe some part are useless for the ZK acceleration. So could you target or give me some answer for this question?
Yeah, so okay, so what we found to be like what's really good about GPUs is that you're basically able to implement okay, so for example, our MSM algorithm, right? It works on on this idea of buckets where you basically like parallelize the entire MSM computation into many buckets. Now with GPUs, I think like this is where they really became like useful, where we were able to use uh, like all these like kernels really efficiently and basically run this algorithm really inside a parallel way. That's where GPUs really shine. So yeah, like that's it. Like I think like what we found most useful about GPUs is that they basically offer massive parallelism without a lot of effort. So for example, like implementing the same thing in FPGAs would be more challenging from the start than doing it with GPUs. So like development times are way faster, I think. So yeah, that's what we really found to be useful about GPUs.
Okay, so in your opinion, so what's the most useless part? So, because we should have if one person want to buy a GPU, so he have to pay a lot of money, right? So, like
Yeah.
we buy a piece of bread, but some part we don't want to eat that. So, in GPU, so which part do you don't want to? You don't want that. Which part?
I'm not sure. Okay, so there's like tensor cores. So I'm not sure if tensor cores are like hard coded into the
Okay.
device.
Okay.
I'm not sure if they're like hard coded into the device or if they're like virtualized. I'm actually not sure about that. But like we can't really use tensor cores.
Okay.
So that's something like again, I'm not sure if that's actually physical hardware in the device. So
Surely.
I'm not sure about that.
Surely. Okay. Thanks for your thanks. And one more question. So I saw your representation. So and I noted the proof time of not the proof time. So the calculation time for MSM so has been reduced by 96, right? Probably 96. And the overall proof time can be reduced by around half. So what prevents the proof time from decreasing as much as MSM time?
Yeah, so the reason that this happens is because we don't run these in parallel. We run them sequentially. The reason that we run them sequentially is because each one of these MSMs took up the whole GPU. So for example, if we had, let's say, 5 GPUs, and each GPU did the MSM like and they all ran in parallel, then I guess like you would see an even more like significant decrease here. But Oh, and also, okay, I think this, okay, the like G2 benchmark here was optimized. So this was cut like, I think down to like 120 milliseconds. So if you had each one of them running on a separate GPU, you would have here like a way smaller result, like maybe like 174 milliseconds, something like that. So that's one of the issues with MSMs, that we found that like you need to run them in sequential order, and you can't. Okay, so for example, here you see they actually run parallel. So when you look at like CPU, like CPU implementation actually runs all these MSMs in parallel and not sequentially. That's why their final result isn't basically the sum. It's like the longest one, basically.
Okay.
Was that clear? Or did I not explain it?
So okay, so could I have one more question? Yeah, so I think I need to. Yeah. Because you know the not only so the MSM is not the whole part of ZK proof, right? So I think so in the ZK proof system, so what part is cannot be accelerated by GPU efficiently? Yeah. So because you Ingonyama do a lot of work on hardware acceleration, so I think your team must have some most advanced understanding in this question.
Yeah, so there are parts that cannot be accelerated. I don't remember them off the top of my head. I can provide a answer for this though. I have to ask the like research team. But for example, one thing that we're looking into is like heterogeneous computing, where we do MSM, like FFT, like polyops, like H function on GPU, and then we do the rest of the computation on CPU in parallel to the GPU, because there are many parts that actually cannot be accelerated, or like not. I mean, they can be like, they basically won't really benefit from from a GPU. If I had the code in front of me now, I can maybe point out some parts, but I can send you a good summary of, like, let's say it's like graph 16, a good summary of parts that cannot be accelerated and better be run on CPU.
Yeah, sure. Okay. Yeah. So, anyone?
Yeah, I have some. Yeah, I have just a really like stupid like question. If we get two GPU, like if I have some snarking operation that I need to do, and I have one GPU, and let's say it takes 10 seconds to do. If I have 100 GPUs, what can I expect? Like how can I start to estimate how much faster can I get by adding more GPUs? Does that make sense?
So yeah, it does. Yeah. So okay, so for example, to find out that like answer, you really need to run benchmarks for your use case. But in general, I would say that, like, for example, looking at like this, like graph 16 and like this circuit, having let's say like for NTT, you're able to put all of them into one GPU and run at 100%. So, for example, maybe add one more GPU and you would like I'm not really sure that it would help with NTT, because they all fit into one GPU anyways. But for example, with MSM, because you need to run 4 and you can only do one at a time, like this is a like really obvious place where you would need more GPUs. So like to answer your question, it's kind of one, like a combination of understanding the algorithm that you need to accelerate, and two, like benchmarking. So like it's hard to say, let's say like given like some algorithm, how many GPUs you need without like researching the algorithm. So, and then also benchmarking it. So yeah, I actually also don't have an answer for like the number of GP. Like if you ask me right now for Graph 16, what's the like optimal number of GPUs? I actually would have to benchmark that because we didn't benchmark that.
But what you're saying is there will be a number, like let's say 100, or I don't know, let's say 10, where if you go past it, you stop getting any improvements. Is that what you're saying?
Yeah,
There's an ideal number.
Yes, because it's like a balance between like how much of your GPU is being used. Like you don't want to have, let's say, 100 GPUs where each one's using 1%. Also, like when you have multiple GPUs, okay, so if you implement some algorithm and you use multiple GPUs, you have different ways of implementing it. So for example, if you do each MSM on GPU, then you would need to like copy the like result back to a CPU, right? Now, if you're doing like some more advanced algorithm, where let's say you split one MSM across multiple GPUs, so like a quarter of the MSM is happening here, a quarter of the MSM is happening here, a quarter is happening here. You need to also like move the data between the GPUs themselves to get the final result. So it's really like a balance between how much of your GPU is being utilized. You would really want like all your GPUs to be utilized to the maximum. So for example, if you have, let's say, like 2 GPUs being utilized to the maximum, and then adding a third one is still everything's being used to the maximum, but when you get to the fifth, 4 are being used to the maximum and one's being used like 50%, and into the sixth it's less and less until you get to a situation where like the GPUs are all running at like 30%, let's say. Like you would want to, I guess, like cut down on GPUs and go back to a version where most of your GPUs are running at 100%.
Okay, can you? Yeah, I wanted to ask about ASICs. Like, where does that fit into the story, and yeah, what do we expect?
Yeah.
What can we expect in the future from that?
Yeah. So okay, so ASICs. Okay, so one of the goals of Ingonyama is to build what's called a ZPU, zero knowledge processing unit. So imagine like you have the GPUs today, and the GPUs are like general compute devices, right? So what Ingonyama wants to build really is like a general ZK compute device. So basically, like think about it like a G, like I guess it's an ASIC that can do general compute. Like it's an actual chip, like a GPU that can do general compute for like ZK. And then you have like tensor cores. So you would have like modular multiplication cores, like instead of like the like AI equivalent, right? So currently there's no ASIC solution in the market. My guess for the future is that, for example, Alio, different ZK miners may have ASICs down the line, but currently most ZK miners are using GPUs just because the cost of developing an ASIC is tremendous. Like it's tens of millions of dollars, and every design change requires. Okay, so for example, let's say that you have the Alio algorithm. You have this ASIC miner, and then Alio changes their algorithm, or like Poseidon 2 comes out, Poseidon 3. Then suddenly your old ASICs become obsolete. You need to upgrade them, right? So currently there's no like ASIC solution on the market, I think, that's like available. It's definitely being worked on. Everyone's working on it. But currently it is not available on the market. But it's definitely like in the works.
Okay, are there any other teams out there that are maybe Ingonyama competitors that you do respect and you think it's worth looking at their work?
I can't really. I don't really know any names of them, but like you can look up hardware acceleration online, and you can see some names. If you look up hardware acceleration, you will find like I guess the top 3 players, along with Ingonyama.
And just final question. Final question on research and where the current research is. What are the hot areas of research today? And like, do you think that people are researching? Like, what are the key kind of areas?
Yeah, so one is MSM, NTT, Poseidon hash, like hashing, especially for Stark, because Stark is very like hash oriented. 2, I guess, like GPU implementations, FPGA implementations. Those are very popular. Like, and then 3, I think a lot of people are working on like combined systems. So, for example, how do you take, let's say, a couple FPGAs and then run proofs on it, or how do you, let's say, like if you look at like Scroll, right? Scroll miner. One of the research, like Ingonyama is doing research on a Scroll miner, and how do you build an efficient Scroll miner? So I think like in terms of hardware acceleration, lots of the research is actually like focused on the like modular multiplication implementations, like because it's a bit different than like prover. Like, okay, if you look at like the like research that's around provers, like Halo 2, Graph 16, like Nova, all of these researchers, they're like more they're like more looking into like constraint systems, right? And like how to optimize for like minimal constraint systems, different like optimizations at the algorithm level. But like hardware people, they're more interested in how many like operations can you do on this piece of hardware, right? So like lots of the hardware like like R&D is basically oriented towards, I guess, getting the like core functions like modular multiplication to run fast on FPGAs, let's say. Cause like FPGAs also, they're kind of like the stepping stone between the GPU and the ASIC. So lots of the prototyping is done on like FPGAs. So you prototype on the FPGA, you get good results, and then if you get like amazing results in a frame, then you would try to go into like producing an ASIC. I hope I answered that question clearly. Cause I kind of like went off some tangents there.
I might ask one more. If you were to take a guess, a wild guess about the first ASIC to do such a thing, what would it be? Like, what would be a good candidate for that's ready? Maybe like if you were to take a guess.
Yeah. Hey, currently I don't know anything on the market. Like there's really like there's some on Twitter, there's some people that like showed some ASICs that they built, but like these ASICs are on very, very old architecture, and they're like on very, very low clock speed. So they're not really fast, and they're not really like it's kind of like experiments. Um so it's hard. I can't really point out a project, I guess. One interesting project though is actually, did you guys ever hear of Urbit and Zorp? So if you look at Urbit and Zorp, that's actually an interesting project. It's like this operating system, and they have their own like bytecode. And then there's this team named Zorp that built this ZK prover around the actual bytecode of that virtual operating system. And what's interesting there is that like their operations, it's like what's interesting there is that they also have this FPGA implementation. Now, I never really tried to run any of it, but it's interesting directions, and it's an interesting experiment because there's like this existing operating system, and there's this and there's basically this like ZK prover that can run the bytecode of that operating system. So it's interesting actually. So Zorp and Urbit, I think are like that's like the most interesting project that I can think of outside of like my day-to-day work, I guess. Yeah. Also, they're like a cool team actually.
All right, seems we don't have any questions for now, but Emmanuel and the team are all on our Telegram chat, and you have the Discord to add on. Any questions, you could feel free to ask there. And if we have more questions coming up, we can also schedule for another session. So thank you so much for today. We'll see you soon.
Yeah, so don't forget to send your Telegram handle so I can add you to the group.
Sure. Thank you.
Thank you guys. Bye.